Temi. I run Babs.ai. Babs is a personal study assistant built specifically for students. And prior to building Babs, I've been working in AI for about 6 years now. So today, I'm going to be showing and sharing with you an idea that is really important, not only for AI or data science, but also for career and for life in general. And that idea is the idea of abstractions. While they're setting this up, I'll start without my slides, so forgive me if it's coming out a bit wonky. Every solution that has been built so far from time immemorial, every solution is an abstraction of some previously existing solution. I'll give an example of the industrial revolutions. The first industrial revolution, we had the steam engines, we could harness heat. And in the second industrial revolution, we built an abstraction over that allowed us to convert or generate that heat using electricity. And in the third industrial revolution, we had software, which is an abstraction over a lot of things. An abstraction over hardware, an abstraction over ideas, an abstraction over images, objects, basically. So in that revolution, if you wanted to create an image, you did not have to paint it manually. You could do that using a software, which would make it faster and more accurate. And now we're in the fourth industrial revolution, the AI revolution. And in the fourth industrial revolution, we're abstracting over the result of the third industrial revolution, and that's data. And it's this idea of abstractions I'm about to share with you. And it's important because it would help you answer the question of just how much math do you need to know to work in AI, to build AI solutions. I like the presentation that, I don't know how many of you were here for that, but I like the presentation that Sam did. And he was talking about high level versus low level. And in the tech world, when we say high level, it's typically boring, simple stuff that has been abstracted away. And low level would mean that it's a bit harder. It takes a lot more detail to understand. And so, high level versus low level, I'm going to give some examples here. And that would help you understand how this idea of abstractions is important to every area of life. First example, organizations. You look at the typical organizational structure, you have some executive, and then you have the management, and then you have the individual contributors. And executive doesn't need to know exactly how many lines of code are in a Python file. Neither does the manager, but the individual contributor kind of needs to know the details of the particular module or the particular package or the particular product they're working on. The manager may not need to know, as I said, a number of lines of code, but they need to understand, on a higher level, they need to understand a broader picture of that product that is being built, the history of the product, the journey, where it's going. Executive needs to understand how that product fits into the business and all that. That's the first example. Second example is the human body, the human anatomy. We're all humans here, so I mean, we're organisms, and this is a very rough, inaccurate, again, inaccurate, because a lot of people are not going to agree. It's a very inaccurate description of the hierarchy of, the abstraction hierarchy of how humans came to be. So we have the human who's with an organism, and then that organism is made up of different organs, and then if you strip down to it, basically at the bottom of that stack, we have cells, right? And multicellular organisms, basically, that's really what we are. And another good example of this is in AI. All of us know how this thing has changed how we do a lot of things. AI abstracts over data in the manner that I discussed earlier. So you have ChatGPT. I'm going to do this with my hand. So you have ChatGPT, Llama, and all these really great, interesting models that are sitting on top of some technology like transformer architecture, which sits on top of something like linear algebra and calculus, which sits on top of something like statistics, and statistics is basically mathematics. I would have shown in the slides, but it's not available right now. Okay, coming up. Thank you. So the idea I'm trying to share with you here is that math is at the very core, at the very low level that Sam mentioned earlier. Very low level of abstraction stack or abstraction hierarchy of multiple domains, multiple industries, and it fits in almost any technology industry that you may be working in. So let's skip a few slides because we've gone over those.
You have simulations, right? Where you're trying to see measure control variables. Yeah. So if I put this, what is going to be simulated?
All right. Sorry.
Right? And then there's causality.
This is another example, very good example. Software stack. So you have your Java application, your mobile application, or whatever. That's sitting on top of some framework like Spring or something like that, which sits on top of your Java JDK, which sitting on top of bytecode, which sitting on top of operating system, and sitting on top of binary, right? And that's a very interesting stack. Wherever you fall on, you can think about how much detail you have to put in to solve a problem in any of those layers. The higher up you are, the easier it is. The further down the stack, it gets a bit more complicated and requires a lot of detail. Organizational stack, biological life, artificial intelligence. So we for AI, for example, we have like 3 different sub-stacks. Got the hardware stack with GPUs and transistors, which sit on top of chemicals, which are basically fundamental particles. Those who study physics would know this. And then for the software, PyTorch is sitting on top of NumPy and SciPy. If you look at PyTorch code or TensorFlow, you find a lot of NumPy dependency. And then NumPy is sitting on top of like Python and C and C++, and all of them are basically bits. Algorithms. You have your data science, which sits on top of statistics, which is basically math. No offense to statisticians. Okay, so I have here a small graphic. Top layers are easy, and they abstract away the details, so you don't have to focus too much on it. Imagine your car had a problem, and you had to understand specifically how the engine works before you solve it. That would be crazy, right? But you don't have to, because that's an abstraction. And then further down, it gets harder. You require more detail to understand it. Well, here's the good thing. You don't have to work at the bottom of the stack. You probably even want to work at the top. Many of the features of the bottom layers of the stack have already been solidified, if you get what I mean. So trying to change for example, the laws of physics. I mean, it's crazy if you can, like Einstein did, but why? And just work on the easy top layer of the stack. And we'll go into more details for specific fields in data and AI.
Your X, your Y, your exogenous,
Okay, one more thing before we go to the next slide. Edge cases. So sometimes the abstractions do not take care of edge cases and they have to like drill down. You find this when you're working on a software product and you have to look into the dependencies that you're using and you find out, oh, this dependency doesn't have this. When we're working on one of our products, we're using a library, a Python library, and basically it's open source, so we had to go to GitHub, clone it, change it, build our own wheel file, and then use that dependency. So sometimes you need an understanding of maybe the next few layers down the stack. It's always helpful.
They have this attachment, this
Now, your job as an individual is to figure out what specific layer or layers of the stack you want to focus on and focus on them. And this is important because if you're all over the place, especially in early stages, it's not very good, except one is like a genius. I mean, we're all geniuses, but like genius. Yeah, it's better to work in the top layers. All right, so the stack for data fields, we'll be picking specific data roles and talking about their stack and what their stack looks like. Business intelligence analysts, you typically need to understand the business problem here. And on top of that, below that, yeah, data analysis and math. For the data analyst, I put in here its tool and concept. Bear in mind that these are summarizations, so they're not really detailed. I mean the stacks as I put them here. A data analyst, you're collecting data, processing it, analyzing large data sets, and you're basically trying to solve business problems using data. And you would typically look into tools like Power BI, Pandas, Excel, Tableau, which sit on top of languages like Python, SQL, R, and you have concepts that you kind of need to understand: data processing, cleaning, data annotation, data structures, and then those sit on top of algorithms, which sits on top of statistics, which is math. For the data engineer, you're ensuring that the right people have the right data. And we got a software stack and a system stack here. Again, it's simplification of the stack. So we have Airflow, Snowflake, Spark, Apache Spark, and those sit on top of Python, SQL. Systems, you need to understand data models, you need to understand logical and physical data models, and those are basically on top of database and database design, and that's a bit more complicated. It's even more complicated when it's distributed systems. That's why that is at the very bottom of the stack. And even this stack sits on top of the regular software stack, like operating systems and binary and all. All right, for machine learning engineers, here is what the stack looks like. You're basically coming up with algorithms, and you want to solve business problems using those algorithms by training models. So your product there is this model, which is basically an equation, a very, very big, giant math equation. And
experts, people who have
That's where that's reflected there in the bottom of the stack with math, which has statistics on top and which has data science on top and
who wants to give me any
yeah,
flavor?
algorithms. For software, you got PyTorch, and below that, as I explained earlier, NumPy, and then on top of that, below that, sorry, Python and C and C++.
Anybody else want to try?
All right. So the core idea here is what I mentioned earlier. Math is at the bottom of every stack, but you don't need to know the details of linear algebra, for example, or differential equations, or all of calculus to solve problems for your company. Why? Because some geniuses somewhere have built tools like PyTorch, like TensorFlow, which are on top of all these other ideas. So trying to work on them and trying to build those, it's like reinventing the wheel, and the question is why? So how do you choose a layer?
Specific method.
There are two
And also,
ideas that I want to share. Think of them as recommendations. There's a lot of ways you could choose what layer of the stack you want to build in. All right, experience-based approach. So here, it's very simple. Early stages of your career, choose the simple things, but there's a caveat. As you go, quickly drill down, because you don't want to stay stuck at the bottom of the stack. You want to go down quickly to the very bottom, because it helps you gain relevance in your industry. It helps you become a domain expert. And yeah, it helps you get promotions and all. And this idea is not just restricted to individuals. It's also businesses. As a business, you want to move to the very bottom of the stack. And that's every CEO's job. Ensure that your business is solving problems that are created by the solutions you're providing. And you typically want to own all layers of the value chain down to from the very beginning to the end. I mean, one person who I respect so much, who has done quite a lot of that, is Elon Musk. And you find that Tesla would build their own batteries, they would build their own AI stack, they would build the hardware on top of which the models are running, and that's just top genius. The second approach is stack adjacency. So the idea here is that you've been working in data science, for example, or data analysis, and you've drilled down to the bottom of that stack. You now understand a lot of math, and you want to transition into a new field, and you look for what's adjacent, what's shared between what shares mathematics or calculus or any area of math that you have learned, and then use that to transition into that field. Here is a very good example. So as a data scientist, I drilled down, now I understand a little bit of calculus and math or linear algebra, and then I can use that to transition into machine learning. And this could work for multiple fields. Again, math is at the very bottom of most industries. If you think about it carefully, even down to psychology, especially when you think about statistics and you're analyzing, you're looking at broad sociology and how people interact, and you can think about the graph data representation of how people interact and how people communicate. It could be a good way to introduce yourself into machine learning with graph neural networks and things like that. So we're coming to the end here. How much math do you need? I can't answer that question for you, but I think that I've tried to share the tools that you need to help yourself make this decision. And it's important because if you understand this concept of abstractions, you can apply it to every area of life outside of career and outside of data. So I hope that I've been helpful to help you think not just about your career, but also about everything and life and how you can think about structures, organizations, people, anything basically. There's always a high level and there's always a low level. You want to be a master, drill down to the bottom. You want to start at the very top, start at the top of the hierarchy, and it just makes things easier for you. And as you go on, quickly, again, drill down to the bottom. As an organization, you want to do that. As a human, everybody, just drill down, but start anyway. Thank you. Once again, my name is Temi. Thank you for having me. Questions? No? Using both the art and science in operation. Okay, so she's asking for practical examples that we can all relate to. Personally, I read research papers and implement them. So like math is at the very core of my work. Fortunately, we haven't announced this yet, so it might be a good thing to do it here. We got access to, via partnership with Intel, we got access to a couple of GPUs, which we're really excited about, which allows us to slowly deviate from OpenAI's API calls and focus on our own machine learning stack, which is great for us. And a lot of the things we have been doing now is collecting data from users and using that to train our own model that sits on top of some GPUs. And then what that really requires is looking a combination of two things: open source and research work, especially in deep learning and large language models specifically. And good examples. So we're leveraging OpenAI, but we realized that we had some issues with accuracy, especially because we needed to save costs by using the 3.5 as opposed to the 4. And then we decided to go open source, which is where Intel came in. And then we took Llama, and in partnership with the Intel engineers, we decided that we were going to pick a few research papers, especially ones that the Intel engineers have been working on, and use that to, especially fine-tuning those models, methods for fine-tuning. One of them is LoRa. I don't know if you've heard about it. It's called LoRa, L-O-R-A, low rank adaptation. And basically, what you're doing is, instead of training a large model, which is large, and it would use a lot of compute, you want to train a much smaller model alongside the large one. And then you're fine-tuning the smaller guy. In simple terms, you're fine-tuning the smaller guy instead of the large one, but then you use both of them together. And then on top of that, there's QLoRa, which uses quantization. And basically, these things are like 16 bits. You drill them down to 8 bits. And if you look at these methods and you read these research papers, you see that there's a lot of math involved. And basically, you want to solve those problems with abstractions that have already been created, like PyTorch. So we use a lot of PyTorch to answer your question. I hope that was concrete enough. Thank you. Anyone have any questions?
You've not verified it. You've not gone to the real world. So the real time matters at times.
Okay, we're saying you could get by with little maths, just like you depend on the abstractions. And there is this saying that goes on around that don't try to reinvent the wheel and stuff like that. But sometimes I try to want to check what is happening under the hood. And when you want to know what is happening under the hood, it means what you are trying to do is, even if you are not reinventing the wheel, you are going through the same stress that someone wants to reinvent the wheel will do, because you are trying to get, or even more, because you are trying to understand this process. And if there will be need for you to make adjustments that you think should be made on it, then you make your own adjustments too. So my question here is, if you want to do something like that, or if that's what, as an individual, if that's what thrills me, is that on its own something that I could dedicate my whole time to, or I could handle it with a career, like a normal machine learning career, machine learning engineering career as well? So I said, trying to reinvent the wheel, in quotes, like the way I explained it. Is it a mission? Is it a profession on its own that will take a whole lot of my time, that I won't be able to do any other career thing if I want to do it, or I can handle the two together?
So his question is, you're trying to drill down to the very bottom of the stack, and it's complex and it requires a lot of your time. Can you do that in addition to things that are much higher up in the stack? Is that what you're saying? Okay, with your day-to-day job, that doesn't require all that math or all that. Okay. Yes, and I would say, actually, that's it. Life stuff. You kind of have to do both if you want to. Again, it's not compulsory. Don't have to learn all the math. But if you really care about what's going on under the hood and you want to build your own PyTorch or your own JAX, then you kind of have to have an understanding of calculus, you have to have an understanding of linear algebra and all that. But yeah, it's good to understand, but it's not a problem if you don't. You'd be better off if you did.